Welcome to the Artificial Intelligence course, A Complete Introduction. In the previous lesson, we already discussed about linear regression and how to apply this technique to predict a continuous value. And today, I will present to you another technique called Logistic Regression, but we will use it for the problem of classification. Now, we start the first part. First of all, I would like to give you a definition of what is binary classification. We start with the use case. Predict students' exam results based on some criteria. And we suppose that we have a training set like this. This data table has 3 columns. The first one shows the IQ score of students. The second one shows their number of study hours. And the last one shows their exam results recorded. There are only 2 possibilities for the results, either passed or failed, so this is a binary decision. Actually, this is just an example dataset, okay? Now, let x1 and x2 denote the input variables of IQ score and study hours respectively. Then, what we expect on the output is that if the exam result is classified or predicted as passed, then we output 1. Otherwise, we output 0. As you see, this problem considers only discrete outputs. It's different from continuous outputs in linear regression problem that you have learned previously. Furthermore, because the output variable has only 2 possible values, that is binary output, so this kind of problem is called binary classification. Oftenly, people use 0 to denote the negative class and 1 to denote the positive class. The 2 words negative and positive are used just for representation. They are not forced to mean something good or bad, okay? Formally, binary classification is the task of classifying the elements of a given set into 2 groups using a classifier, that is a processor or a set of classification rules. Now let's draw the data in the training set. Because there are 2 input variables, so we have 2 axes. The horizontal axis represents the number of study hours, and the vertical axis represents the IQ score of student. Just for the purpose of illustration, we suppose that the data in the training set are distributed like this. More precisely, the green points represent the data points classified as passed, and the brown points represent the data points classified as failed. For example, this data point shows someone who is not so very intelligent but they passed the exam because they have spent a lot of time studying. And you should know that if you are joining an AI self-study class like this, I strongly believe that you are both intelligent and working very hard, just me. In a binary classification problem, we want that the dataset must be well separated. More intuitively, in this example, I can draw a straight line like this to separate the data points into 2 sets, each one for a class. If you already learned a little about algebra, you should know that this straight line can be represented by the following equation. phi0 plus phi1x1 plus phi2x2 equals 0, where phi0, phi1, and phi2 are called parameters of the equation. And if you don't forget some basic math, you will know that the straight line represented by this equation will divide the space into 2 sides. For one side, given any point x1, x2, we have phi0 plus phi1 x1 plus phi2 x2 is greater than 0. And for the other side, any point x1, x2 belonging to this side will satisfy. phi0 plus phi1 x1 plus phi2 x2 is smaller than 0. Concretely, this side of the line satisfies one of those 2 inequalities, and we suppose that it is phi0 plus phi1 x1 plus phi2 x2 is greater than 0, and this side satisfies the opposite inequality. Therefore, in order to well separate the data points, we want as many green points as possible to satisfy this inequality, so that so that they will all belong to the same side of the straight line. Conversely, we want as many brown points as possible to satisfy this inequality so that they all belong to this side of the straight line. So, from this analysis, we propose the following idea. We first learn the parameters phi0, phi1, and phi2 such that the line phi0 plus phi1x1 plus phi2x2 equals 0 well separates the training set as shown by the figure on the left. Then, for any input x1, x2, we predict the output y by the following rule. If phi0 plus phi1x1 plus phi2x2 is greater than or equal to 0, then y is predicted as 1. In the opposite case, y is predicted as 0. And the straight line constructed from such phi0, phi1, and phi2 is called the decision boundary of this binary classification problem. And this is the idea of decision boundary. As you have seen, the decision boundary in the current example is simply a straight line represented by a linear equation. To give you more intuition about decision boundary, imagine that we have more input features, for example 3. Then the decision boundary will not be a straight line anymore, but a plane, for example like this. In this case, we add phi3x3 to the linear equation. Or look at this example. If the data points are distributed like this, then a straight line can never separate the data points, but the decision boundary should be something like this. It is definitely a nonlinear boundary, and its equation looks like this one, where we have to add polynomial features x1 squared and x2 squared. However, in this case, if we create other features x3 equal to x1 squared and x4 equal to x2 squared, then this equation can be rewritten in a linear form like this, as you already see this idea in the lesson about multiple linear regression. So, decision boundary is defined as a hypersurface, for example a line, a plane, a hyperplane, etc., represented by an implicit equation, linear or nonlinear, that divide the underlying space into two sets, one for each class label. And in binary classification problem, we assign the same label to the data points belonging to the same side of the decision boundary. Okay? Generically, a classification problem may have n input variables represented by a feature vector x consisting of x0, x1, x2 up to xn. Note that x0 is always equal to 1, just for the convenience of a representation. In binary classification, the output y has only two possible values, 0 and 1. Then, to solve this binary classification problem, our approach is to learn the parameter vector phi consisting of phi0, phi1, phi2 up to phin, so that the decision boundary for the classification will be phi0 x0 plus phi1 x1 plus up to phin xn equals 0. And this equation is equivalent to vector phi dot vector x equals 0. Note that we just use the dot product to simplify the above equation. By the way, I would like to inform you that later sometimes I will say phi instead of vector phi or x instead of vector x if they do not make any confusion, okay? Just for the simplification of speaking. Finally, once we find the decision boundary, for any input xi, we predict the output yi by the following rule. If phi dot xi is greater than or equal to 0, then we predict y as 1. Otherwise, we predict y as 0. By this way, we construct a linear classifier for the binary classification problem. However, we have to answer the following question. How to learn such parameters phi0, phi1 up to phin? And here, is the proposed idea. First step, we define a function f of x parameterized by phi such that for any input xi, if phi.xi is greater than or equal to 0, then f of xi will predict yi as 1. If phi.xi is less than 0, then f of xi will predict yi as 0. Furthermore, f of xi will also give a prediction score on the output yi. From that, we can evaluate the certainties of the decisions. Next step, we define the cost function c of phi, which calculates the total error of prediction using f of x over the training set. Finally, we learn the parameter vector phi that minimize this cost function c, and there are the expected parameters to construct the decision boundary. In the next lesson, I will show you how to define the function f of x and the cost function c